Okay, so this video is actually mainly for the discussion for the question number 4 that we discussed from the previous video. So there's also some additional exercise for the chapter capacitor. So let's discuss for the question number 1, which is the question number 4 that we discussed from the previous video. Okay, so the charge capacitor. So this question is continued from the question number 4. Okay, so the charge capacitor in A is then discharged through the circuit connected to a resistor of the 10 kilovolt times 10 to the power of 3, since kilo is the times 10 to the power of 3. So okay, so this capacitor basically is allowed to be discharged. So for the question A, I'll redo again, since although I have done from the previous video. So determine the time taken for the charge in the capacitor to decrease to its half of its initial value. So so this is charge. So the formula for the discharging circuits will be Q naught multiplied by E to the power of negative T over CR. Okay, so this is half of its initial value, means is 1 should be 1 over 2 Q naught. So Q naught E, and this is T, and the C, the capacitance of the capacitor. Okay, I think I should write it. Okay, there's no enough space, so this is E, negative T. So the capacitance I didn't write in this question, so I'll see from the original questions. So the capacitance, okay, I think we should calculate again for the capacitance. So C is actually epsilon naught A over D. So the epsilon naught A, the permittivity of free space, should be 8.85 times 10 to the power of negative 12. So the A given from the questions is 0.24 meters square divided by the plate of separation, which is 0.65 times 10 to the power negative 2. Okay, so what I have here is the capacitance, which is 3.268 times 10 to the power negative 10, which is farad. Okay, so my capacitance will be 3.268 times 10 to the power negative 10 farad. So this is 268 times 10 to the power negative 10. Okay, so the resistor is 10 times 10 to the power of 3. Okay, so finally I can calculate the time taken for the electrical charges to decrease to its half of its initial value. So basically Q naught and Q naught can be cancelled. So what I get for the time taken, so let me just calculate for a while, times negative 10 times 10 to the power of 3. So finally what I get is actually 2.265 times 10 to the power negative 6, and this is seconds. Okay, so for the question B, Okay, so for the question B, the B is actually the question that confused me from the previous video. So we will solve in this. Okay, the current after 2.0 microseconds. So T basically is 2.0 times 10 to the power negative 6 seconds. So the current. So for the discharging circuits, we know that the current should be I is equals to I naught E negative T over CR. So we know that we did not have this value, which is the I naught. So what we need to do is actually derive. So since based on the Ohm's law, we know that V naught is actually equals to I naught R. So what I need to do is actually derive in terms of I naught. So what I have here is actually V naught over R. So this is T divided by CR. Okay, so the potential difference. Okay, let me just observe for a while. So is it correct? Okay, so the potential difference, the initial potential difference given by the question is actually 0.8 times 10 to the power of 3. So the question that I type here is actually not given the full information. So the full, if you wish to know the full information, you should watch the from the previous video. So the full information is actually contained from that video. So from here, I just briefly observe from my book. Okay, so the initial potential difference will be 0.8 times 10 to the power of 3 volts. So the resistance is 10 times 10 to the power of 3. So the the T given here is 2.0 times 10 to the power negative 6. Okay, let me just erase this one. So, okay, the capacitance, which remain constant. So the capacitance is 3.268 times 10 to the power of negative 10. So the resistor, which is the same, so the resistor will be 10 times 10 to the power of 3. Okay, so what will be our value? 0.8 times 10 to the power of 3. So 10 times 10 to the power of 3 multiplied by the exponential negative 2 times 10 to the power negative 6. So divided by 3.268 times 10 to the power negative 10. So 10 times 10 to the power of 3. So finally what I get here is 0.0434 ampere. So basically this is the way that we calculate the current if we did not have the did not have the initial current based on the information given. Okay, so if we do not have the information, so what we need to do is to think and derive the formula from this initial current. So the initial current based on the Ohm's law we have V naught is equals to I naught R. So I naught will be equals to V naught divided by R. So that is the way that we derive the initial current. Alright, so let's move on to the question number 2. So this is actually the additional question as I mentioned just now. Okay, so the circuit below show a parallel plate capacitor connected to a power supply. So based on the diagram, okay, let me just erase this one for a bit. Okay, this one will do. Okay, so based on the diagram, we can see that the plate of separation for the capacitor initially is D. So after separating more further, so the plate of separation become 2D. Okay, let me just highlight. Okay, so basically this one is okay. Alright, so this one is D and this one is 2D. Alright, so with the power supply is still connected, the plate of the capacitor, so the power supply is still connected, it means that the capacitor is actually in the condition of charging. So the plates of the capacitor are then separated further until the distance between the two plates is doubled. So find the ratio of the energy stored in the capacitor as shown in figure 1 to the energy stored as shown in figure 2. So this one is the error. Okay, so basically the question required for the ratio of the energy stored in figure 1 to the ratio of energy stored in the figure 2. So the energy stored, the formula for the energy stored, we know that is actually U is equals to 1 over 2 CV squared. Okay, so what we need to do to find out to know that, or I can say to determine which one should we derive it. So either it is C, the capacitance, or the potential difference across the capacitor. So in this case, what we're gonna do is to derive the capacitance, which is epsilon naught A over D, while for the potential difference we remain it. So why is this so? This is because when the plate is separated further, the influence that how should I describe this? The effect will causes the capacitor, the capacitance of the capacitor to be bigger. So based on the C, epsilon naught A over D. So if the okay, so then just now I mentioned bigger is actually the mistakes. So when the distance of plate separation gets further, and hence the capacitance of the capacitor will decrease. So the capacitance of the capacitor is the one that will be affected when the plate separation is doubled. Okay, as for the potential difference, so since we know that the electric field strength is actually equals to the potential difference across the capacitor divided by plate separation. So the V is ED. So we actually can sub this equation into here, but we do not do that. This is because in this case our potential difference the potential difference across the capacitor is actually constant. The constant means that the battery is actually keeps supplying the electrical charges to the capacitor. So hence the potential difference will not the potential difference will be constant instead of manipulated variable, and hence so I can conclude that the capacitance is the one that will be affected. So based on this relation, I can say that U is actually inversely proportional to the plate of separation. Okay, so the ratio of figure 1 to the ratio of figure 2. So since they have the inversely proportional relation, hence this one is D2 and this one is D1. Okay, so D2, what I have here is actually 2D and this one is D, and finally the ratio of U1 to U2 is 2. So this is the way that we how should I say, that we relate both of the initial energy stored and the final energy stored when the plate separation is separated further. Alright, so okay, let me observe for a while. Okay, so alright, so this is the correct answer. Okay, so this is number 3. Alright, so I think I should do some notes again. So I repeat again for these questions. So this V, the value of the potential difference, although the capacitor is actually charging and the potential difference will be increased, of course. So but in this case, the capacitor, the plate separation is getting further. So when I should say in this case, initially when the plate separation is D and the capacitance is actually charging, and hence the potential difference is getting higher. When the suppose the potential difference getting higher in this case, but the plate separation is getting bigger. Okay, so this causes the potential difference to be constant. So this is why we say that the potential difference is actually constant. So this one is considered to be the additional notes. Alright, so let's move on to the question number 3. Okay, let me just... Alright, so... Okay, so this is question number 3. A capacitor, okay, let me just zoom it for a bit. Okay, let me just... Alright, so this is number 3A. A capacitor of the capacitance C is 120 times 10 to the power negative 6 farad is connected to the 10-volt battery. So this one should denote as the V0. So this one is 10 volts, and then remove. It is then connected to a 20 kilo ohm resistor and a switch. Okay, so in this statement, I can know that initially the capacitor is actually charging. So when the battery is removed, it is then connected to 20 kilo ohm resistor. So this statement, From this statement, I can know that the capacitor initially is charging and then is then allowed to be discharged. Okay, so what is the current in the circuits at the moment when the switch is closed? So we know that from the previous video we discussed about when the moment the switch is closed, so we can consider the time taken to be discharging is actually 0 since the switch is just about to close. Okay, so for the current, the formula for the current is actually this one, I naught e to the power negative t over cr. So since the t is 0, and hence what we have here, I is actually equals to I naught, which is maximum current. So maximum current, what we have here is actually V over R, as we discussed from the previous question. So this is V naught over R. So V naught from the battery, which is 10 volts. So the resistor is 20 times 10 to the power of 3. Okay, so to be note that this V naught initially is from the battery. So after the capacitor is fully charged, so hence the potential difference across the capacitor is 10 volts, which is same as the volt from the battery initially. Okay, so this is the 10 volt, 20 times 10 to the power of 3. Okay, so what I have here is 5.00 times 10 to the power negative 4, and this is ampere. Okay, so this is A. And how long will it take to be discharged when the potential difference across the capacitor drops to 1.5 volts? Okay, so the question is actually asking the how long. It means that the time taken for the potential difference to drop to 1.5 volt. So for the discharging circuits, what we have here, the potential difference is V naught E negative T divided by CR. So this is 1.5 of course, and this is 10. And T is the one that we need to find. So the capacitance of the capacitor given here is 120 times 10 to the power negative 6. So as for the resistor, 20 times 10 to the power of 3. Okay, so finally what I can find that the time taken from 10 volt to 1.5 volt. Okay, so this is ln 1.5 divided by 10 times negative 120 times 10 to the power negative 6, 20 times 10 to the power of 3. So finally the answer will be 4.553 seconds. Okay, so the capacitor needs for actually almost 5 seconds to drop the potential difference from 10 volts to 1.5 volts. So this is the way that we calculate. Alright, so I think we have done for all the 3 questions. So I think we stop here now. So if there are any question need to be asked, please comment below this video, and I'll see you next time. Thank you. Bye.